means that we will probably be able to actually cover a lot more than I expected, because I did this before and it was like just 15. We only made it past slide 15. But yeah, ask me many questions. I know you are very smart people, so I am not worried about time really. But yeah, let's get started. Optimal transport, moving sandcastles in the air. It's a class of problems where you basically have a sandcastle. Right? We will formalize this, but I'm just trying to give an intuitive understanding of what we are trying to achieve. Right? You have sandcastle A or alpha, and I want to move this sandcastle to some position beta. Right? And in this case, the drawing is not very good, but the shape could be the same or it could be different. Now, you know the cost of moving a particle from here to position here, and similarly for all of the particles of sand, you know how to move them, or the cost of moving them to all of the positions in your target space. Now, the question that you have is, how can I use this information to, or like the information of moving, of the information of a cost of moving particle from position in the alpha, like in the alpha pile to the beta pile or the target pile, to minimize the cost. So how do I optimally transport this pile of sand from alpha to beta? That's the whole idea. And whatever a combination of particle movements from one to the other satisfies this problem is basically your optimal transport problem. So
just to
yeah.
this clearly, the idea here is you don't want to individually move the data points, but you want to be able to move the whole data set as efficiently as possible.
We will talk about the relevance with the data set, and this is we'll talk about relevance with deep learning, but for now don't think about deep learning at all.
Not as a data set as deep learning, I'm just saying like there's data, like data points.
Sure, yeah, okay.
Or like a cluster of individual points, right? And you're trying to move that sum of points, like that group of points, like sand points, somewhere else without having to move individually the points.
Yeah, right? So you are moving the points individually, right? Each of the points are being moved individually, but what combination of points need to go where is the main question. Like for example, I have this particle over here, moving this particle from position 1 to say position 2 can cost me 3, right? Some arbitrary number. And then this one, I can move it to this arbitrary point and it could cost me 4. And now the cost of moving point 1 to position 2 versus position 3 over here is different, right? And you basically want to figure out what is the optimal combination of the transportation to basically get the pile of sand from alpha to beta while using the minimum cost. So the cost of moving each particle basically adds up till you basically get the resultant target beta. And we want to figure out which combination of movements is the most optimal. And we'll talk about the connection to deep learning, because that one clearly is very important to us, right? So the important question is, why should we, as people who are very interested in deep learning, care about this problem? We start with this. I originally intended to start with this analogy of Monge, who likes playing with sandcastles, and he thinks about what is the most efficient way of moving this marvelous sandcastle alpha to my house in beta, right? And optimal transport was born. That's the general problem description. Why you should care? 1, you like playing with sandcastles and want to take it home. 2, you are interested in any of the following research foci, and now this is where deep learning comes in. First is a neural style transfer. We have a input image over here of some lakeside with a bunch of houses, and I have a reference image of some art piece. I want to get the image A in the style of the reference image, and one way of doing this is to basically calculate the color map or the distribution of the pixel values within the reference image. So for example, 10% of the image is the color yellow, or like some specific shade of yellow, and then you take your input image and say what is the minimum cost of transportation of the original pixels in this image to become to match the same distribution as my reference image. And basically, by calculating what that minimum cost is and transporting each individual pixel to the target pixel that you get basically after computing the optimal transport plan is your stylized image. So that is one application.
Is it a distribution of colors or is it a distribution of like some latent style?
Of colors. So RGB, the RGB distribution. So you have R of 3 of colors from 0 to 255, right? So you basically compute the color map of this image and you compute. Hello.
I'm so sorry.
You're good. You're good. We
I
double.
know, dude. I was like working.
We double the attendance in a fraction of a second. This is
No, she was leaving. I was like, yo, pull up.
Okay.
Do we miss anything important?
No. I'll just re-say it. It's not that complicated. The basic idea is you have a pile of sand, and this pile of sand is called alpha.
I was just telling her about that. Yeah. Okay.
What?
I was just telling her about that.
What?
Moving sand.
I was telling her about sand.
Oh.
Yeah.
Okay. Like from here?
No, like we were just talking about optimal transfer. And it's like, oh, basically you have like one pile of sand, you have another one. It's like, what's the optimal way of like changing this pile of sand?
Wait.
Yeah.
Yeah, that's exactly correct. You were talking about, why were you all talking about optimal transport? Or why not? But
We were just talking about it.
That's so cool. Okay, awesome.
Okay, so I guess we're caught up.
Yeah, you all already know that. Then you're missing nothing. Wonderful. Okay, so yeah, removing sand from one place to another, I want to do it in the most optimal way possible. That is the problem that is stated by optimal transport. The other thing is that we want to figure out is why are we supposed to care about this class of problems? And it has a lot of applications in deep learning, very specifically for computing loss functions that on inputs or model outputs that are geometric in nature. So I'll discuss exactly what that is and why traditional models fail, but one very big application of optimal transport is in those class of problems. So one application is neural style transfer. I have a reference image of this river and a bunch of houses, and I want to stylize it in the style of this art piece. And the way you go about it is you basically compute a distribution of all of the colors. So you have RGB from 0 to 255, and you compute the distribution of colors that are present within this image, and also compute the distribution of colors present in this image. Then you compute the transportation cost of moving distribution alpha to distribution beta while minimizing the transportation cost. And by minimizing transportation costs, what you effectively do is you constrain the structure of the model or keep of the original image and convert it to the stylized version while retaining some of the distinct features that make the original image the original image. Question?
Yeah. What's like a good way of like visualizing the distribution of colors?
Oh, you would just go.
You just like count like the pixels of like you know like here's like R and RGB, so how it makes like 3 distributions, right?
Yeah.
So you just like basically just count like split it in a scale, and then like for every single pixel, just like put a tick basically.
Exactly.
Okay.
Right. Yeah. So you have 3 values over here for each of these, and that is effectively your distribution of color in this particular.
And the cost, I'm assuming, is a cost to change like the total sum or like the squared sum of.
That is custom. Basically, you can set it to be whatever, but it has to satisfy properties of a distance from point to point. So the natural choice is squared or like Euclidean distance or p norm. So that's exactly right. You're thinking in the right direction, definitely. I will have to check. I think it's still valid. Yeah, but we can check. Anyways, that is the general idea behind optimal transport for this specific case. Some examples that I will maybe gloss over a little bit less in detail. Sentence similarity. You have one sentence that's Obama speaks to the media in Illinois, or the president greets the press in Chicago. Obviously, Obama is not the president of the United States as of 2024 or 25, but the idea is consistent, where the meaning is effectively the same, and you want to basically calculate the distance of Obama with president, speaks with greets, Illinois with Chicago, and press with media. And you effectively get the distance of document 1 to document 2, and you can use that in order to compare how close two sentences are.
I thought he stopped being president in 2016.
What? He stopped? Yeah. So exactly. I was trying to think, but I didn't know, and I didn't want to guess. So yeah, as of 2015, this is true, but maybe not in 2025. Anyways, graph neural networks, better representation learning. You have the graph structure, and that remains consistent, but towards the end, usually in graph convolutional networks, you effectively just concatenate the representations on various nodes. That is not the optimal way of doing this because you lose some geometric intuition within the actual graph structure, and a better way was basically discovered using optimal transport, and that improves the representations that are generated by the graph neural network, and that helps it to be more distributionally robust. Medical imaging is another one. This is pure optimization, where you have the same model architecture, but it is able to detect tissue loss in the same set of images in a much better way than just standard entropy or divergence based loss formulations. So optimal transport, basically it induces a distance over the input space rather than a divergence, and that has some interesting properties which we will get into, which allow for it to basically identify better parameters versus your standard divergence based optimization setting. Finally, robust point cloud matching, where you have point clouds where a large percentage of your points have disappeared. In this scenario, there are a couple of approaches. This is initialization, and these are kind of two ways of matching the point clouds. CPD and CRIP-ICP do not work as well as the proposed method which use optimal transport. So the main thing that kind of connects all of these is that you have geometric problems and you need to solve them in an efficient way, and optimal transport does very well to make sure that that happens. So that's the motivation. Now let us get into some of the actual formalisms, and that starts with the Monge problem. So Monge was the original person from our story who wanted to move the sandcastle, and that effectively starts with the formal problem that he proposed. So we begin with a probability simplex. So we have some n-dimensional simplex. Each element is positive, and the sum of each of those elements comes out to 1. You define over this a discrete probability measure. Alpha x is just basically if I have a histogram, that is one way to also think about it. I have position x1, x2, and x3, and the amount of mass that I have at positions x1, x2, and x3 effectively just creates the histogram. So this will be A1, A2, and A3, and if I want to compute the position at some x, you effectively are just summing up over all of the x's in this, so from 1, 2, and 3, and you compute the value of the weight, so at this position, and you add it if chi, which is basically just identity function, not identity, indicator function of x in your x. So x over here refers to the input from here, and x1, x2, x3 is this entire set over here. So basically, if you have this in your set, then you would basically add that value. So this is just one way to describe a discrete probability measure. Yeah.
Just to make sure I'm following. So basically, in the first one, we're kind of describing a PDF over such that like every single column, you have n discrete values such that they all just sum up to 1. Correct?
Okay.
And then in the bottom, we're saying, okay, now over this PDF, we want to like sum up some range of like discrete like values, Right?
Well, this is just kind of a way of saying I want to query how much probability mass is present at point x1, point x2, point x3,
right.
or some.
So basically, just to make sure I'm following. So basically, you're saying like, I have like this like PDF over like the integers, right? And it all sums up to 1. And then the chi is like basically applying a mask, saying I'm going to sum up the actual the weight from these specific integers.
Yes, exactly.
Okay.
Yeah, from these. Yeah, you got it.
So why does it have to be like this? Like, why does it have to be? So x in this case like a set, right? Is that correct?
Yes, x is a set.
Okay.
That is exactly correct. Yeah.
Just to be more clear, at least for myself, so we're saying that each value or data set like has a probability of being there. For example, pixel has a certain probability of being its specific color. Is that what you're saying in your discrete probability?
Okay, no. So let's maybe not think about data set so much, because we still have not optimal transport comes, or like deep learning application of optimal transport comes very much later into this, because Monge problem you can't actually use this for optimal transport, or like for deep learning problems, and we'll get into why in a second. But the idea is to just think of it like a histogram, right? You have positions, and at each position you have a particular value, and this is basically a functional way of just of querying the value at a particular point x.
So what I'm saying is like for the image, for example, the pixel, what is the probability of having that pixel of that specific color?
You would basically assign the position of the point within the image, or like within your distribution, and the RGB value. Okay, wait. Let me think about this. If I were to create a discrete probability measure from this, yes, exactly. So you have R of 3, and the probability of the value that you basically empirically compute of it being a particular color is the probability mass that you assign to that color. Similarly for the reference image, and then you would compute the transport map, optimal transport map from original to stylized version.
Okay.
Right. Okay. Awesome.
This only works for if we have enough information to create the distribution, right?
Pardon?
Like this only works if we have enough data to create the distribution. Like here we wouldn't have probability of, let's say, I don't know, like a weird purple that's just not the pixel.
It would just be 0. Like it can be, your probability has to be just non-negative, obviously. So if there is a weird purple that just does not exist in this image, that will just have probability measure or probability mass 0. And all of the colors that are present will have probability positive mass. Same for this case, and then we want to transform this to here, basically, while using the least energy possible. Sweet. Any more questions? Okay, cool. So we have a discrete probability measure, and we are going to talk about discrete probability measures today because it allows us to use intuition. It's just more intuitive to look at discrete probability measures versus continuous ones. The framework that we will discuss today works both for continuous and a discrete setting, but because we are going to mainly talk about the discrete setting, I just wanted to point out that this is in fact true, and it is not limited to just the set of problems that we will discuss today, and that it usually, to get to the continuous case, it's more work and it is a bit more unintuitive, but it is very meaningful nonetheless. We are using computational optimal transport, which is the first link from the intro slide over here. So if you find this interesting, I definitely recommend checking this out after this presentation. Okay. Alright, so let's get to the actual problem itself. Monge now asks us to transfer measure alpha to a new measure beta, effectively this thing that we had discussed earlier, while also minimizing the total cost of transportation. We represent alpha and beta both as discrete probability measures, and now we also introduce the notion of the cost. So I mentioned earlier that we know the cost of moving, say, point over here, 1 to 2 has a cost of 3, and moving it to this point over here has a cost of 4. right? So now we have to introduce some formalism to basically denote this in a more sensible way, and that's basically just a cost matrix. So you have the total cost of moving mass from xi to yj represented as a matrix from where I goes from 1 through n, j goes from 1 through m, and Cij is basically cost of moving xi to yj, or mass from mass present in xi to mass present in yj. Mass present in xi2 position yj. Sorry. All right. So now we define a map from the space of x to the space of y that just tells us what we are going to move where, and this becomes our transfer plan. So now we can formally actually define the assignment objective that was introduced by Monge in the 1700s, where you want to minimize your cost of transportation by optimizing over your transport plan. So you have all of the possible transport plans in the world. How can you identify or determine which is the most efficient way of transferring probability mass alpha to, or like discrete measure alpha to discrete measure beta? Okay, so that is a problem that we have in our hands. If n is equal to m, t will just become your set of permutations. So moving points from one location to the other. So two visual examples of optimal transport. We have this over here where we have x1 and x2, and the valid transportation plan could be basically either. So you could move x2 to y1, or you could move x2 to y2, and the x1 was just going to be the conjugate of that. So x1 will move to y1 if x2 moves to y2, and vice versa. The transportation cost is the same. So one important observation from this is that the transportation cost is not unique. Then another problem that looks a little bit more complicated, you have a bunch of the a bunch of the x's in blues from 4 through 7 that all basically move into y1, and crucially these are valid transportation plans. So there are a couple of interesting things we can observe just from these two examples. Firstly, optimal transport map is not necessarily unique, right? This is from the example on the left. And the other one is that this current formulation doesn't allow us to mass split. So, for example, if we have x5 and x2 combined into one mass, call it x prime, then you will no longer have any valid transportation map, because now you cannot break up x5 and x2 and move one to y2 and the other to y sub 1, right? Like that point has to move to the other, and that constrains our possible solution set pretty significantly. The other important thing to note is that if m is greater than n, then there is no feasible transport plan, and this follows immediately from 2, where we don't have any mass splitting. So imagine I have 8, or if you basically want to kind of inverse the problem, I have to go from all of the reds to the blues, the y's to the x's. I cannot split up all of the y1s, and it cannot go to multiple places at once. Therefore, it is not possible to basically transport in the reverse direction. Yes?
Curious. Do you know if this NP hard or NP complete by any chance?
This is a combinatorial problem, so it is O of n factorial complicated to solve. I think it is NP hard, but I cannot tell you for sure. Okay. Complexity scales sharply, and the consequence of this is that optimization landscape is non-convex. Question?
I have a problem with that statement.
Okay.
Because this looks, I might be wrong, but it looks very, very similar to a transshipment problem, or at least, at the very least, an assignment problem.
Yeah.
Which can be wrong with simplex, which means that it is convex.
That is not true. That is not true.
It is not an assignment problem?
This is an assignment problem, but this is the optimization landscape for this problem is not convex, which means you can't use this is not a linear programming problem. This is the exact thing that we will solve, however. You are certainly thinking on the right track, which is awesome. That's all I had to say about Monge's assignment problem. But these are all pretty significant problems, and mass splitting is basically the main cause of this issue. And we will find out how to solve this in one fell swoop with the Kantorovich problem in the next slide, or like slide 12. Before that, one additional observation that we did not mention in these first four is that for any valid transportation plan, we have the mass conservation property that is satisfied, which means that all of the x's that go to a particular y sum up to the mass of that particular y. If that does not happen, that means that it is not a valid transport map, and computing the cost means nothing for us because we have not transferred alpha to beta anymore. So we basically have this over here, this equation over here, which it basically describes the same thing in a mathematical way. For every mass in y, or every mass b sub j in y, we basically sum up all of the masses that are present in the input that transport to point y sub j, and that becomes our resultant target mass. And the push forward operator is basically one way of transporting the entire measure space alpha to measure space beta in one fell swoop. So we discussed the cost matrix and the fact that we know the cost of transporting point 1 to point 2 over here. And if you want to do this process for all of the points in alpha to all of the points in our target measure beta, we can just describe a way of doing that, and that is the T sharp over there, which is just the transport of one measure space of alpha to the other measure space of beta. And that is basically just represented the same way. Question?
So T sharp consists of all of the individual transport plans for every single one?
No, it is for a specific transport plan. It is the application of a specific transport plan from measure alpha to beta.
So basically, it's like, so T sharp is a specific transfer plan?
Yes, it is a specific transport plan.
What's the difference between the two?
Yeah, so the transport plan is a map, right? It is a map from x to y.
Yeah.
So I will give you, I will give the transport map x sub I, and it will tell you move this point, move x sub I or all of the mass in x sub I to y sub j, right? But I want to do this process for the entire measure for alpha, right?
Right.
And doing that is basically just the push forward operation. So
basically, like push forward would be like, it'll have from every single x1 through xn, it will have a map from every single one of them to
yes,
y.
Exactly. So basically, if I want to just say, the main idea is just this bit over here, b is equal to t sharp alpha, or beta is equal to t sharp alpha, which is just us saying you take this entire pile of sand and move it all the way to beta, rather than just discussing it with like one point at a time. Discuss the entire pile of sand at once, or move the entire pile of sand at once. So that's the push forward operation. Then there is another operation called the pull back operation. This is different from push forward, even though semantically it sounds like the direct inverse. And the pullback operator basically is an operation on the masses rather than an operation on the measure space, where you have a set of continuous functions, or a 1 minute, let me see, t raised to the power sharp, I don't know what that is called, but I'll just call it t pullback, from the continuous space of y to the continuous space of x, just mapped as a composition of some function g. And these two operators are in fact intertwined in the sense that you can either integrate over the push forward of measure alpha using the transport map t, or you can pull back your function that you are attempting to measure with the pull back operator into the original measure space x or alpha, and then you can compute the integral over this original measure. It is not the inverse of the transport plan where you move from beta to alpha, but you are moving the function that you are computing an integral over from beta to alpha. Question?
What is G and what is GD?
What is G and what is?
GD.
Oh, G, sorry, that is G and D of, this is just computing integral, right? Like this is, there's supposed to be a space. It is Y, G, D.
Where are you writing?
Oh.
Oh, I see. Okay, and what is G then?
Yeah, G is just a continuous function.
Of what?
G is from the set is a function from a set of continuous functions.
It's just any function.
Any continuous function. Yeah, it's arbitrary.
So where does G live, in Y or X?
I think G is this is something that confused me as well. It is the set of continuous functions from space X to Y, like that transforms. That transforms Y to X.
So G lives in Y, C of Y.
Okay, yeah.
That's what it looks like, because you have alpha is m of x, which I think is true from what you're saying.
One more time, sorry.
Alpha has to live in m of x, so from A.
Yes,
it has to be
exactly.
C1.
Yeah. Okay, question.
I'm still like kind of confused about like what is happening
Okay.
because you have t raised to t superscript sharp
Yeah.
is mapping from the mass over y to the mass of x, which is different from the measure.
Yes, or like the basically the map of moving points, or the okay. So we have
This like t sub sharp. It's telling you, hey, here's like some way like moving all the points in the distribution alpha to all the points in distribution in beta, right?
Right.
That's what t sub sharp does, right?
Yeah.
So I'm just like confused. Like, what is then like t like because like in t superscript sharp looks really similar to like an inverse, but it's not the inverse.
Yeah, it is not the inverse because the inverse would be to move the beta.
Right, from beta to alpha.
Yes,
Right,
exactly.
but that's like I'm just confused. Like, can you talk a little more like what C is exactly?
Sure. Okay. So we are integrating over. So I think I need to talk about Lebesgue integral. How are we familiar with Lebesgue integral?
Wait, which integral, sir?
Lebesgue integral. Okay. Let's see. It should not be that crazy. We have first off, is this in the?
We can see.
Why is it so difficult to? Okay. We have the notion of a step function where you basically have a set where the value of your function is consistent. So I have c sub 1 over here and then c sub 2 over here. Okay, and the c1 or like the input, let's call this x over here, it has the value of c1 over a set a1 and it has the value of c2 over a set a2, correct? And you basically x becomes the union of a1, a2 and then so on and so forth for all of the possible sets of sets where your function has this particular value, right? Now, this is effectively what a step function is, where you basically say that this function has a constant value over this set a sub 1 through a sub infinity. Okay, and you do it until it covers the entire input space x. Now we can compute the integral of this function, that is effectively just the volume that you give to all of the sets that have the same value c1. So I will do c1 and times a measure of a1 union a2, because that is where c1 is contained, and add that with c2's value and a measure of a2. So think of this mu measure operator as just the like a measure of length, for example. So if we have b1 a1 b2 a2, this is similar to like the standard Riemann integral, right? So this you could imagine as just b1 minus a1 plus b2 minus a2, and so on and so forth. So the idea is that you can define it with a specific set of properties. This map mu, which goes from what happened?
Sorry, you're saying A1 union A2, but you didn't include A2.
Oh, sorry. Yeah, my bad. I didn't realize I called this entire thing just one set. So yeah, measure of A1 is just B1 minus A1 and B2 minus A2, right? That's consistent. Thank you. And this is the notion of an integral. This is the Lebesgue integral. right? You are effectively integrating over the range rather than integrating over the domain, right? That's the big difference. So this over here, what we are seeing, this is also the Lebesgue integral, where we have d alpha is the measure of, or like is basically just this thing over here. Similarly for this bit. So we have a function over which we want to compute the integral. This function has to be continuous, and the way push forward and pull back operators are connected is you have your original space alpha that gets pushed forward to beta. G works on this space y, you integrate over it, and that this integration is basically just summing up over each of the measures. So we are doing C1 and C1 beta A1 and so on and so forth in the language of this first bit equation, and then the other equation over here is basically we are composing a function before G. So we are doing G compose some pullback operation, and that operation we are basically the range of this is basically what we are integrating over with respect to the original measure alpha. So that is where the distinction occurs. We are integrating over two different measures, and push forward is converting the measure, pull back is converting the function. Is this clear now? Does it make sense? Kind of?
It makes enough sense that will we be lost if we don't fully understand?
Well, the important one is push forward. If you don't understand push forward, that's a concern because you will need it. Pull back is more so important to just understanding the specific of push forward, because you won't use pull back, but we will use push forward.
Okay, so push forward is how you transport like one distribution to the next. It's just the total, like how you do it.
Yeah.
Okay, that's just the check.
Okay. Awesome.
Sorry, I know we're spending some time, but like, why isn't G is there a function G that's non-linear in this case? Because it seems that G has to be linear, right? Because you're saying G of f of x equals to f of G of x, right?
Clarify one more time. I don't see why G is linear.
I was really stupid. Please ignore what I said. Okay.
It's okay.
Thank you.
Alright, okay. More questions? Okay. Back to slide 10, where we observed the fact that the Monge's assignment problem is not very easy to solve. Katarovich saw this, he saw all of the problems and decided that he was going to take matters in his own hands and propose a fix. And he proposed a fix by basically making the problem a little bit more complex by relaxing the problem. So the key idea was he will relax the deterministic constraint and get a probabilistic transport, which means basically now we are going to allow mass splitting, which previously was not possible. And this is very relevant because now this becomes a linear problem, and what Alex said about using the simplex algorithm to solve it can come into play, and we can actually solve this in an efficient manner, at least much more efficient compared to the Monge assignment problem. Now, instead of a transport map where you basically say move xi to yj, we define a family of coupling matrices where each P in R of n cross m is a valid coupling. Basically, we want that same original mass conservation constraint that we discussed earlier by using this coupling matrix that just says transport this much of your mass to x0, x1, x2, all the way through xm for each input. And by doing this, you effectively just get your total amount of mass that is transported from A to B, or alpha to beta. And the idea behind the constraint over here, we basically say if I sum up along m, I should get the original mass in A, and or like the vector of original masses in A, and the transpose of that would get you just the vector of masses in B, or the distribution in B. So now our new optimization objective becomes sum P in the set of all of the possible valid couplings, we want to still minimize our cost of transportation, and this is just the Frobenius inner product. So you're basically just flattening everything and then just computing inner product. It's just summing everything element-wise basically, and you get the total cost of transportation now. So this is very, very important, right? Because we went from an original problem that actually admitted fewer solutions to a problem that admits n number of solutions, and this becomes this, at least on the surface, right? When I was initially learning about this, I was like, oh, this is very, very silly. Why we just made everything much more harder for ourselves. Previously, I could use some silly trick to remove all of the invalid transport maps from the set of all permutations, maybe get some like minor improvement. But Kantorovich said that we will solve this by like in several orders of magnitude quicker by converting this into a linear problem, because each of the constraints that we have over here are linear constraints, and the objective that we are trying to minimize is also linear. So big observation is now this is a linear program, and we can use more sophisticated methods in order to solve the Kantorovich problem. And not just that, okay, maybe we'll talk about that in a second. But this is what visually the same thing looks like. You have alpha, beta with uniform mass on each of the distributions, and that is basically equivalent to the Monge's assignment problem, because you see that basically every point within alpha is going to a single point in beta, versus the other case where you have non-uniform weights, and in this case you can see that there are multiple points that are being transported from alpha to one particular beta, and in cases where one is basic, or like many cases where you can see alpha basically getting split up, which is exactly what the Kantorovich relaxation allows. Question?
Can you show a little confused about the original Monge assignment problem, where specifically we stopped that?
Okay, here or the slide before this?
Like in the actual minimization problem, where do we stop splitting?
We do not split at all. We are not allowed to split.
But where do we do that stop? Like I'm a little confused about that. Is it because of the way that the mapping?
Oh yeah, exactly. It's a transport map, right? So you basically are transporting, or like a good way to see that is through this over here, the equation phi. Because I am transporting for each index I am transporting only those points where transporting I gets me to y, right? Mm-hmm. So the transport plan will you will give it as input x1, and it will tell you move this to y1. You cannot if you give it x1, it won't tell you move half to y1 and then half to y2, right? It's just not possible to. Oh, come on. Okay, it's kind of like this, where you give t x1, it will tell you y1, right? If you give it x1, this is not what it will give you. It won't give you half goes to y1, half goes to y2, right? It just tells you where to go. It gives you 1 point at the end and not the mass. Question?
No, sorry, blurred out for a second.
Okay. Yeah. Okay. Anyways, but that does that explain why this mass splitting is kind of blocked in the Monge assignment problem?
Yeah, that makes sense. But now it's basically transshifted problem.
Okay, I'm not familiar with that. So if you say that one is solvable with linear programming, I think there may be some differences in those two problems. But yeah, I know for certain that this one is non-convex and we cannot solve it using linear.
Right, now it makes a lot more sense. Yeah, you can't split it. It is non-convex.
Right. Yeah. So it is just a direct combinatorial problem, and now we go to the relaxation, and the relaxation is not a combinatorial problem. It is a linear program, and we can solve linear program in a more intelligent way. So before we get into the linear programming aspects also, the important things that I wanted to mention about the Kantorovich relaxation is if we restrict P to just be the permutation matrix and have each weight be uniform, we are recovering Monge map, right? And since in our LC, which stands for our Kantorovich problem, we can basically set it to be anything or an extension of our original permutation you effectively can state that if you are minimizing the Cantor-Roach problem, you are effectively also doing better than solving the Monge's assignment problem. And if in fact the optimal solution is a permutation, you will recover that as well, because the permutation is a superset of it is a subset of all of the possible P, right? So you can express permutation as within your set of valid couplings P. Therefore, by solving the Cantor-Roach problem, you are also considering every single case in which a direct permutation is your optimal solution. So the Cantor-Roach relaxation is tight. That is the main conclusion from this. And each coupling is symmetric, which means that you can also invert the transportation plan automatically, which means you go from alpha to beta, beta to alpha. It's both are possible in every single setting. That's awesome. So,
sorry.
Yeah.
This is basically like moving from integer programming to non-integer programming in a way.
Oh yeah, that's a very, very good way to put it, because you now are basically saying instead of a sort of a 0-1 map where you either go to this point or do not go to this point, and you have a sparse combination, which is effectively what permutation matrix becomes. You can say that assign some percentage of mass to some percentage of mass from xi to yj1 and then yj2 and so on and so forth. Right?
Okay, that makes sense.
Okay, awesome. How much time do we have? I will talk about dual formulation. Give me 1 second. Let me just kind of understand. Okay, I can maybe finish talking about the Cantor-Roach dual today, and then next week we can talk about the rest. Okay, the headline news from the Cantor-Roach relaxation is now our optimization objective is a linear program, and the implication of this is that it can be solved in n raised to 2.5 log n. So it is much more efficient than what we originally had, which was in factorial. The problem is now convex. This follows from the fact that it is a linear program, and the optimal transport problem now has a dual, which is basically another linear program whose optimal value upper bounds the optimal value of the primal. And this conjugate problem is very relevant in traditional linear programming literature, because you are only basically looking at a subset of the total possible or the total valid solutions when you are computing or when you are solving for the optimal value within the linear program, and you want to establish that what you have at the end of your answer is in fact the optimal, and you cannot improve on it without basically going through the process of solving for every single other problem. Or like every single possible combination. And one way to do this is by basically solving for the dual, which is another linear program that upper bounds the optimal of the primal. If it is exactly equal, then the problem has an optimal solution. So if we know the problem has an optimal solution, we can basically choose which problem we want to solve, and by solving either one of the problems, we will end up at the same answer. This is the strong duality theorem. Questions? Okay. This is exactly what I said. Wonderful. Go ahead.
It's not necessarily true, because solving either primal or dual is basically the same thing.
Yeah.
So like, there's not an easier problem, right?
I will talk about an example where we will use the dual rather than the primal.
Yeah,
It's some problems. Pardon?
Very sure, like computationally, primal and dual take as many steps, at least with simplex.
No, well, but we will not talk about the simplex specifically. Simplex is one part of the picture, but this is actually still too complicated for us. So the main problems, the main algorithms that are used is the syncon algorithm, wherein this is now a convex problem. It is good, but we need to basically make it strictly convex, and the syncon, the work done to basically derive the syncon algorithm performs entropy regularization from the starting point to make the search space strictly convex, and then it uses a fixed point algorithm in order to actually compute the final solution in quicker than n raised to 2.5 log n time. and the algorithm that we will discuss next week probably is the next week definitely is sliced Wasserstein distance, which just projects things into random directions, and we will talk about the details of that. But it is n log n time solution basically. So simplex is a big improvement from the original, but it is still too complex for deep learning cases because we have to solve optimal transport at every single iteration, and that has to be done very, very efficiently. What is the time? It's 8:57. Yeah. Okay. I will finish up the. Okay. Yeah. We can maybe talk about this from the next week because there is a lot to get into. But yeah. Thank you so much. A question?
Yeah. Sorry, I'm still a little bit confused about what is simplex. What is simplex? What is a dual? What is a primal? I'm confused about those three terms.
It's the most beautiful thing in mathematics.
I don't know what it is though.
Okay, yeah. Simplex is simply just a probability polynomial. You have vectors. Where is pen? Okay. You have a vector. What is happening?
I can explain to you if you want afterwards. Yeah. The visual way, because take CS left when you're like you'll go through it with pure linear algebra. It's fucking up.
Yeah. Well, the idea is just you have every element x2 through xn. This is like just softmax effectively. Okay. You are pushing everything into a probability space, which means all of these need to be greater than 0 and need to sum up to 1. Yeah. So exactly what softmax is doing, it is constraining it to this polytope, which is
and then what does that give you?
A probability vector.
Right. What do you do afterward?
What, pardon?
What do you do afterward? Like you get a probability vector, like simplex step 1 and you get a probability vector.
Yes. Then step 2, you compute, you obtain a discrete measure on top of the input. This, you have simplex over there.
Oh, okay. You end up at this point. Okay, gotcha.
Yeah, and then you create a discrete measure using the simplex.
Okay.
Right.
And then what is a dual and what is a primal then?
That is linear programming specific. Probably Alex will be very happy to talk about it. But your basic idea behind linear program is that you have a series of linear constraints. So I have one constraint. Imagine this book is R of 2, right? I have one constraint like going along this line, one constraint going along this line, one here, one here, one here, and after you get all these constraints, you basically obtain this hull of solutions. And this is your feasible set, right? Okay. This is where you can feasibly get this use any point within this space while satisfying all of the constraints. Right? This is a potential solution. Exactly. Now, in addition to these set of constraints, you also have the optimization objective, which in itself is effectively
within like the constraint space. What is like the optimal point, right?
Yeah, you want to find out in this constraint space what is the optimal point. But the interesting idea, right, behind solving just this thing by itself is not very helpful, right? You effectively get on top of the set of constraints, you have a vector effectively, which is your direction of increase or your direction of decrease, and you basically go along this vector and kind of sketch like something orthogonal to this over here, and you move along this direction from start all the way to the finish, and whichever is the last point that you land on is your optimal solution. So one interesting aspect is that the optimal solution always is at one of these extrema. So 1, 2, 3, 4. You instead of computing instead of computing the entire space of solutions, you only have to compute these points, and you can compare which one is better. And with the simplex algorithm, it even gives you like a direction in which to move in order to maximize your increase. And at the end, whichever point you end up across is your point of optima. One degenerate case is if I have a constraint such that the entire face ends up being the last point, then you will just have a full face of optimal solutions, which means it is not going to be unique. But that's the general motivation behind the linear program and why it makes it much more easier to compute the optima versus a combinatorial problem that's non-convex. So the convexity of this problem is very, very relevant. And the primal is just the original problem, the minimizing problem that we are.
Okay. So primal's original, the dual is converting it to this problem.
Oh no. This is our original problem. You can look at it.
Okay.
This is just a linear program. So this is arbitrary.
Right. Then what is a dual then?
A primal is a set of constraints and an optimization.
So you use them like together. So primal is a set of constraints. Dual is the actual problem. Right?
No. That's what I'm saying. The dual is just a different problem, right?
Okay.
It is a different problem, but it has a unique property of upper bounding the primal. So you basic.
It makes sense.
Yeah, you have a set of linear constraints and the vector that gives you the direction of maximum increase or the direction of increase for the primal, and you have the same set of things for the dual as well. And whatever optimal solution you get for your primal will be lesser than or equal to your solution of the solution of your dual problem. So this is the form of our primal equation 10, and the form of the dual, which we will cover next week, is equation number 13.